Hi guys, this is the second episode of our Marine Electricity Handbook, Chapter 13. Chapter 13 is dedicated to AC motors, DC motors, reversible motors AC and DC, and transformers. In the previous episode, basically we covered DC motors. DC motor, how the DC motor works, how reverse DC motors, low current and high current. In this episode, we are going to talk about AC motors, induction motors, how the AC motor works, and what is the procedure to reverse the rotation on AC motors, high current and low current. And the episode number 3 will be focused in transformers, isolated transformers, step-up transformers, and step-down transformers. Okay, now we are going to start with the fundamentals, the basic concept of AC motors. In order to understand the AC motors easily, we are going to refresh quickly the concept about the DC motor, the electromagnets on the rotor and permanent magnets on the stator, and we are going to use that concept to introduce induction motors. Okay, the rotor have electromagnets. The electromagnets have magnetic properties only when the brushes, those are the brushes, the springs, the carbon, and that terminal is connected with the ignition switch. We have two brushes, one here for the positive and other here for the negative. When the brushes are in permanent contact with the slip rings, the magnets are strong, and when the magnets are spinning, send electrons, jumped electrons by centrifugal force into the coil, and the coil registers positive and negative. The life of the production of electricity in the alternator depends on the quality of the excitation. If the excitation is good from the battery, from the ignition switch, the power produced is strong. If the excitation is not good because the slip rings are contaminated with oil or dirty in between the brush and the slip rings, the excitation is poor, bad excitation, and the output power is not good. For that reason, you need periodically send the alternator to the machine shop in order to replace the brushes and clean the slip rings and produce better excitation and, of course, excellent output power. Alright, suppose each time that the rotor, one positive and one negative terminals are in front of the coil, one cycle is produced. When one positive and one negative pass in front of the coil, one cycle is produced. The next positive and negative produce other cycle. The next correct. Each positive and negative in front of the coil produce one cycle, two cycles, three cycles. And this is the frequency. The frequency is the amount of cycles in 1 second. The frequency of the American power is 60 cycles. What is the meaning of that? In American power, I have 60 cycles in 1 second. In European power, I have 50 cycles in 1 second. And we are going to study in other episodes the formula to calculate the frequency. Frequency is equal to the number of poles times the RPMs divided by 120. Those are the number of poles. In this particular case, this alternator have 1, 2, 3, 4, 5, 6, 14 poles. This alternator have 14 poles. There are other alternators with 4 poles, with 6 poles, with 2 poles. The majority of the generators, 99% of the generators, they have 4 poles on the rotor. For that reason, if I have 4 poles in the rotor, in order to get 60 Hertz for American power, 60 cycles, each cycle is 1 Hertz. In order to get 60 Hertz, I need 1800 RPMs. For that reason, in order to produce American power with a generator with 4 poles, I need run the generator at 1800 RPMs constantly. What about 50 Hertz for European power? For 50 Hertz, with 4 poles on the rotor, you need to run the generator at 1500 RPMs. I explained that formula in details in other episode of the chapter 10. Okay, right now we have AC current, and now we are going to explain AC motors and DC motors. The DC motors are clear. The DC motors are basically permanent magnets on the stator and electromagnets on the rotor. Immediately, the electromagnets are powered from the ignition switch on the slip rings. The electromagnets in front of the permanent magnets produce the rotation. Depending on the polarity of the power coming in, the rotor spin in this direction or this direction. That's simple. Those are DC motors. The DC motors works with the principle of electromagnetism. Electromagnets in the rotor and permanent magnets on the stator, or vice versa. In some cases, the rotor is permanent magnets and the electromagnets are on the stator. It's exactly the same. Those are DC motors. Now we are going to explain AC motors. The AC motors work with a similar principle. The AC motors work with similar principle, but electromagnets in a rotor and permanent magnets on the stator, or vice versa. But those magnets depend of the electromagnetic force produced for the current. The AC motors are divided in single-phase motor, double-phase, and three-phase motors. The people have too much question about what motor is more efficient, the single-phase motor in comparison with the double-phase or the three-phase motor. And I explain that situation with a simple example. Suppose that you have an engine with only one piston, and you need to move the crankshaft with your hand in order to produce the explosion. Okay, if you have only one piston, only one hand, you need to put too much effort to move the crankshaft. What happens if I replace the crankshaft of that engine for two pistons? Two people moving, one person in one and the other one in the other crank pin. Oh, is better. This is two-phase. What happens if I replace the crankshaft for other crankshaft with three pistons and I put three people to move the crankshaft? Oh, it's perfect. Oh, for that reason you say, my V8 engine with 8 pistons, the movement is soft. Oh, the fourth cylinder is a little hard. Oh, I have a motor with only 2 pistons and the sound is too loud and it's hard. Start and stop the engine. Oh, I have a motor with only 1 piston. Start the engine is hard and stop the engine is hard because it's too much effort at the beginning and at the end. It's exactly the same. If you have a motor, electric motor, single phase, the consumption in amps to move the shaft of the motor is too much. If you have a motor with double phase, is better. If you have a motor with 3 phase, the consumption in amps is less. For that reason, the people say if you replace your old appliance, single phase, for new appliance, double phase or 3 phase, the consumption in amps reduce dramatically and the bill, the monthly bill will be less for you every month. Yeah? Yes. Double phase or 3 phase motors are more efficient than single phase. The consumption in amps of a 3 phase motor and 2 phase motor is less than the consumption in amps of a single phase motor. In general terms, the single phase motors, because they need too much force at the beginning to start, they have internally double winding two windings in series, and one of the windings have a capacitor. This is the capacitor used to start the engine at the beginning. Immediately the motor is running, that capacitor is disconnected, and the motor continue running with the second winding. In the picture, in the annex picture that you see right now, you can see the double winding. The first winding is 90 degrees with respect to the second winding, and the second winding have a capacitor. When the capacitor is saturated, the second winding is disconnected, and the motor continue running only with the first winding. Okay, this is the example. This motor is a single phase motor, and this is the capacitor. The capacitor used only at the beginning to jump, to produce an extra voltage in order to start the motor. All the single phase motor, AC motors, they have an start capacitor, and the capacitor is used only to start. What is the symptom when the start capacitor in a motor is damaged? The symptom is that the motor is humming and it's difficult to start the motor. Probably if you held with your hand on the pulley, the motor continue running. If you remove the cover and you check the capacitor, probably the capacitor is exploded, or the capacitor is too hot, or the capacitor expand because the capacitor is damaged. What is the procedure to check the capacitors? Right now I am going to explain the procedure to check the capacitor. To check a capacitor, you need a voltmeter, and you need to select the voltmeter in the function capacitors. What is the symbol for a capacitor? This is the symbol for a capacitor. That's the symbol for capacitors. What is the unit for capacitors? The unit is farads, microfarads, or nanofarads, or picofarads. Normally the capacitors are rated in microfarads. Okay, I want to check a capacitor. You need a pliers to disconnect both terminals with a pliers, not with the fingers. You need a piece of wire to produce a charge on the capacitor in order to discharge the capacitor. When you have the capacitor outside, you can check on the label. In this particular case, the capacitor is in between, the capacity in farads is in between 189 and 227 microfarads. In between 189 and 227. Okay. After I discharge the capacitor with a piece of wire in between those terminals, I can check. I select my multimeter in capacitors. Let me explain the procedure. The voltmeter is off. Right now I go to this function. In this position there are two functions. The first one is for diodes, and the yellow one is for capacitors. Okay, I need the second one. I go over there, and now I press the yellow button, and I have the capacitors. Okay, and they say nanofarads. Okay, we are going to check how many farads I have here. And right now they have 205 microfarads. If you remember, this is 205. The capacity is in between 189 and 227, and I have 205. This capacitor is in good condition. If the reading is superior or less, you need to replace the capacitor for other one with the same characteristics. This is the only way to check a capacitor. You need a voltmeter selected on the functions diodes. You need to remove the capacitor, discharge the capacitor, and after that check the capacity in farads and verify if the capacity is according with the label. If the capacity is lower or superior than the range of the label, you need to replace the capacitor for other one exactly the same. Never less. A little more probably, but never less. I recommend replace the capacitor for other one with exactly the same characteristics. Once again, you check the capacitor, the capacitor is damaged, you replace for the new one, and right now you can connect the capacitor again, and you put the cover, and right now your single phase motor is perfect. This is a single phase motor, AC motors. There are AC motors 3-phase or double phase, like this: phase 1, phase 2, phase 3, neutral and ground. Phase 1, phase 2, phase 3, neutral and ground. The majority of the 3-phase motor, they have a label on the control box. In order to connect, depending on the connection, you can get in the output high voltage, low voltage, high torque, low torque, high speed, low speed. The 3-phase motor can be configured for high speed, low speed, high torque or low torque, depending how you connect the phases and how you connect the neutral with respect to the phases. Right now, I am going to explain the procedure to reverse rotation in AC motors. What is the procedure to reverse rotation in a 3-phase motor? Basically, you need to switch 2 phases. Suppose that you have 3 phases, A, B, and C. You can switch A with B, or B with C, or A with C. Doesn't matter. You switch 2 phases, and immediately the motor reverses the rotation. How can you do that during the operation of the motor? It's simple. You can use contactors. The only way to reverse rotation in a 3-phase AC induction motors is with contactors. And right now, I am going to explain what is the meaning of contactors. 3-phase reverse rotation. The properly way to reverse rotation in a 3-phase motor is by means of contactors. The contactor is basically a breaker, the 3-phase breakers, with a couple of inputs for the signal. The signal should be AC or DC. For example, this is not properly a contactor, but it's exactly the same. It's a breaker, a 3-phase breaker, with 2 inputs on the side for the signal. What is the function of the signal? Open and close the breaker. Open and close the breaker. Where is coming that signal? It's a remote signal. That signal, once again, is coming from the flybridge, from the pilot helm, and that signal could be DC signal or AC signal, low current signals. A contactor is a remotely activated breaker. The remote activation could be a low current AC or DC signal. The signal enter here, AC or DC, and those are the 3 phases. And the rest is a typical breaker. How can we install those contactors? How is the wiring to connect a 3-phase motor with the contactors in order to reverse the rotation? I have an schematic that I prepared for use. In this schematic, if you check the schematic, I have the main breaker. That's the main breaker that you have in your AC panel. And this is the AC power. The AC power is coming from the source of the power, 3 phases. And this is the output of the main breaker. The output of the main breaker enter in a couple of contactors. I have 2 contactors here, 3 inputs, 3 outputs, 3 inputs, 3 outputs. Okay, the first contactor is for clockwise rotation, and the second contactor probably for counterclock. Okay, the first contactor have 3 inputs: black, red, and blue. The black one, the first position of the first contactor is connected with the first position of the second contactor. Black with black in first position. The second one, the red one, in the first contactor goes into the third one in the second contactor. And the third one in the first contactor go into the second one in the second contactor. That's the switch. I am going to switch the phase 2 and the phase 3 in the second contactor. Okay, and the output is exactly the same. 1 with 1, 2 with 2, and 3 with 3. And the phase number 1 is the black one. The phase number 2 should be the red one. and the phase number 3 is the blue one. Those are the phases that enter in the motor in order to reverse the rotation. And the signals. In this particular case, those contactors are DC remotely activated. Okay, the activation is DC. I have a couple of push buttons, normally open contactor, push buttons, and I am going to activate those contactors with a DC signal coming in DC signal. This is the positive bus bar of my DC panel, and that's the positive bus bar receives the power from the batteries. Okay, the positive enter in the middle in between both contactors, and from the output of the second contactor I activate the contactor number 2, and from the output of the second push buttons I activate the first contactor. When I press this button, I activate the clockwise contactor. When I press the second push buttons, I activate the counterclock contactor. This is the procedure to use contactors and push buttons. You can use normally open or normally closed buttons. It's simple with the normally open momentary push buttons. When I press this one, the motor rotates in one direction. When I press the second one, the motor rotates in the other direction. This is perfect for windlass. This is perfect for bow thrusters. And yes, I can replace those push buttons for a joystick. In one position, I send the signal for this contactor. In the other position, I send the signal for the other contactor. This is exactly the procedure to connect contactors in order to reverse rotation in AC motors, 3-phase motors. Remember, the procedure to reverse rotation in DC motors, high current motors, is with a solenoid control box or with a couple of relays that I explained in the previous episode.